All right, so today we get to bring our notion of implicit equations, thinking of variables with respect to time, into real world scenarios, which actually turns out to be kind of a fun thing. It's not easy, frankly, but it's sort of satisfying, fun in the sense that it's not easy, but you can get results that actually have some real world meaning. So here, imagine we've got a spherical balloon that's being filled with air at a constant rate of 2 cubic centimeters per second. I mean, if you just took a balloon and you attached it to something that was pushing air into it, it is conceivable that that something that was pushing air into it was doing it so at a constant rate. And it's conceivable that the balloon would sort of grow then according to that. And then one question that we have here is, if we're pushing air in at this rate, how fast is our balloon growing in radius when the radius is 3 centimeters? And this is an interesting question too, because if you think about it, initially when the balloon is very small, this 2 cubic centimeters of air is going to swell the balloon quite a bit. But once the balloon gets large, that 2 cubic centimeters is only going to swell the balloon a small margin. So the amount that the radius is changing with respect to time is itself changing. Early on, the radius is changing fairly quickly because the balloon is very small and 2 cubic centimeters is a very large portion of its volume. But eventually, as the balloon gets very large, 2 cubic centimeters might be a relatively small amount of the balloon's volume, and the radius will only change a small amount. So the rate of change of the radius is itself changing, and that is what we want to nail down. How fast is our radius changing when our balloon is 3 centimeters? Okay, so now when you think about this, you're like, man, where the hell am I going to start? Well, we have to come up with some way to relate these facts to one another, and if we can come up with some sort of relation between the facts, we can use that relation and our knowledge of calculus, thinking of those variables changing with respect to time, because they are, frankly, and then we can nail down a solution. So first, note the balloon's being filled with air, and the air is coming in at 2 cubic centimeters per second. This 2 cubic centimeters per second is how much the volume of the balloon is changing with respect to time. So this is the change in our volume with respect to time. How much is the volume of our balloon changing every second? Well, because we're pumping air in at 2 cubic centimeters per second, the change in volume with respect to time is 2 cubic centimeters per second. To answer the question of how fast the radius is increasing, the thing that we're trying to find out is, how does the radius change with respect to time? And now as soon as I write these things out, you say, okay, we have known information about the change in the volume of the balloon. We are trying to find information about the change in the radius of the balloon. Is there any way that we can relate volume of balloon to radius of balloon? Because if we had some relation between volume and radius, we could exploit that relation to come up with a relation between the change in the radius over time and the change in the volume over time. So, question, is there a relation between radius and volume with our balloon? And the answer is yes, because our balloon is a sphere. Because our balloon is a sphere, we know that we have volume of a sphere is 4/3 pi r cubed. And check it out. Here is something that relates volume and radius. Here is something that is now an implicit equation that we could imply our implicit derivative techniques to get dVs and dRs into the game. So if we take the derivative here, we're going to get derivative of v is 1. That's a derivative with respect to v. Derivative on the other side, 4/3 and pi are just numbers. The only letter on the right-hand side is the r. So when we take the derivative of that r cubed, that's going to become 3r squared. But the 3 that we bring down is going to cancel with the 3 that's in the denominator of the 4/3. And we're just going to end up with 4 pi r squared. Oh, but that was a derivative with respect to r, so let's tack on a dr. And moreover, using the techniques that we saw last time, rather than just thinking of this as a dv and a dr, and we're not really interested in dv over dr, dr over dv. We're thinking of these things as changing with respect to time. Let's divide both by dt to now get us in terms of the variables with respect to the situation of interest, which is to say the volume is changing with respect to time, the radius is changing with respect to time, and well, here we have the situation. So now we've got a relation, not just of the v and the r, but of the dv and the dr. Now the question is, can we use the known information to figure out what we want to know? Because we want to know dr over dt. But the thing is, we know what dv over dt is, that's 2. So we can plug 2 in for dv over dt. And hell, on the other side now, we just have a 4 pi, and then we got r squared times dr over dt. And the question then is, well, if we just knew what r was, the only thing that would remain not as a number in our expression would be the very thing that we were trying to find. And if the only thing that would not be a number in your expression is the very thing that you're trying to find, then you could find what that thing is by solving for it. So, okay, what is r? R is the radius. Do we know the radius? Yeah, actually we do, right? Because the radius was 3 centimeters, so r is 3. And so when we plug in r equals 3, we're not just going to get dr dt in general, we're going to get dr dt at the specific instant in time that r was 3. Because remember, as we discussed earlier, whenever the radius is small, the balloon's going to be growing very quickly. Whenever the radius is large, the balloon's going to be growing less quickly, in spite of the fact that the volume being pumped in is at a constant rate. Well, okay, well, the long story short here is, whenever you run the numbers on this, you get 2 equal to, 3 squared is 9, 9 times 4 pi is 36 pi, times dr dt. But if you want to get dr dt by itself, because you do, because you're trying to answer the question of how fast is the radius changing, you're trying to find the change in the radius with respect to time, divide both sides by 36 pi, and you're going to get 1 over 18 pi, and well, there you go. To be thoughtful about this, we probably should include a unit, because 1 over 18 pi doesn't accurately describe how the radius is changing without thinking of what the radius unit is and what the time unit is. But the radius was being measured in centimeters, and the time was being measured in seconds. So if we put that information together, we've got it. And so we've been able to address precisely what the change in the radius is at the instant that the radius is 3. And see, if you check it out here, if we were looking at an instant in time when the radius was something other than 3, we would be plugging a number other than 3 into our expression. If we were plugging 5 into our expression, then rather than dividing by 9, we'd be dividing by 25. Or rather than dividing by 9 times 4, we'd be dividing by 25 times 4, which would give us a smaller value, which is what we would expect, right? Because as the balloon got bigger, the change in the radius was smaller. But the long story short is, this is doable. So we look at our original problem, we assess the information that we have with respect to our mathematical expressions, and then we try to find a relation between the variables of interest. Once we have the relation, we use calculus to get ourselves an expression that is accurately assessing the change of our variables with respect to time. We use all of the known information that we have at our disposal in order to solve for the thing that we're after, and once we've got it, well, we've got it.